Imagine a digital world where the hidden math that protects our money, our privacy, even our agreements suddenly just breaks.
Mm,
That's really the challenge quantum computing is throwing at, well, the foundations of digital trust,
yeah,
especially for something like blockchain.
right. It's a pretty fundamental challenge.
Today, we're doing a deep dive into, I think, a really urgent question. How are blockchains, Bitcoin, Ethereum, how will they actually survive the quantum era?
Yeah.
You might not even realize it, but the security of, well, everything from your online bank to your crypto relies on algorithms that quantum computers could potentially just shatter.
And we're going to try and unpack that today. Look at
Huh.
exactly how quantum computing threatens the blockchains we know now.
Okay.
And then, crucially, look at the two main paths people are exploring to build resilience. There's the post-quantum way and then the quantum blockchain idea.
Two different approaches.
Exactly. We'll get into the science, the real-world effects, and, maybe what's coming down the line.
So what does this all actually mean for you and for the future of decentralized trust? Let's find out.
Okay, so before we dive into the threat, maybe we should quickly recap what parts of current blockchains are actually vulnerable.
Good idea.
Like, take Bitcoin. The security really hangs on a couple of key things, right?
Yeah, definitely. You've got the public-private key pairs, which are basically your address and your way to sign off on transactions.
Right, ownership.
Exactly. And how those keys are generated, often using things like RSA or, more commonly now, elliptic curve cryptography, ECC. That's core to proving you own your coins.
Okay.
And then you have the hash functions, like SHA-256 in Bitcoin. They link the blocks together, creating that chain.
The immutability part.
Precisely. Each block points back to the last one using its hash, its fingerprint.
Yeah.
Messing with an old block means recalculating everything after it, which is super hard, especially with proof of work making it expensive.
And smart contracts, too. They rely on all this underlying crypto. Oh, absolutely. Those if this then that agreements coded onto the blockchain, they lean heavily on the security of the signatures and the integrity of the chain itself.
Okay, so that's the setup. Security based on math problems that are just incredibly hard for today's computers.
Right. Practically impossible in human timescales?
Right. Here comes the quantum twist.
Exactly. This is where quantum computers change the game. They bring new algorithms that can, well, slice through these impossible problems much, much faster.
Okay, so what are these quantum algorithms we need to worry about?
The two really big ones are Shor's algorithm and Grover's algorithm.
Let's start with Shor's. What does it do?
Shor's is kind of the headline act here. Its power lies in factoring large numbers very efficiently and also solving something called the discrete logarithm problem.
And why is that bad for blockchain?
Because those are the exact mathematical problems that underpin the security of RSA and ECC, the public key systems we just talked about.
Ah, the keys for signatures and addresses.
Exactly. So imagine an attacker sees your transaction on a public blockchain. They get your public key. With a powerful enough quantum computer running Shor's, they could figure out your private key from that public key.
And then they can spend your money.
Precisely. They can sign transactions as if they were you. It completely breaks the ownership model.
Wow. And is this theoretical or?
The algorithm is proven. The hardware isn't quite there yet for, say, breaking Bitcoin keys today, but the threat is real. Shor's could theoretically break RSA 2048, a common standard, in maybe minutes or hours. A classical computer would need, well, longer than the age of the universe.
That's staggering. Which coins are vulnerable? You mentioned Bitcoin.
Yeah, Bitcoin, Ethereum, Zcash, Litecoin, Monero. Basically, any blockchain that uses RSA or standard ECC for its public key cryptography is vulnerable to Shor's.
Okay, that Shor's breaking the keys. What about the other one, Grover's? How does that threaten things?
Grover's is different. It offers what's called a quadratic speedup for searching unsorted databases. Think of it like finding a specific name in a giant phone book much faster.
Okay, so how does that apply to blockchain? Searching for what?
It mainly applies to the hashing part. While hash functions themselves, like SHA-256, are generally considered more resistant to quantum attacks than public key crypto, Grover's could speed up the process of finding the right nonce in proof-of-work mining.
Ah, the mining puzzle.
Right. An attacker using Grover's could potentially find blocks much faster than honest miners. This could let them dominate mining rewards, or worse, give them a much better shot at a 51% attack.
Where they control the network and could rewrite history.
Potentially, yeah. They could try to build a longer chain in secret and then broadcast it, replacing the legitimate one. It makes that attack more feasible, computationally speaking.
But you said it's less of a threat than Shor's?
Generally, yes. For current major blockchains like Bitcoin and Ethereum, the consensus is that Shor's is the more immediate and existential threat because it breaks the core ownership mechanism. Grover's offers a speed up, but it's quadratic, not the exponential leap Shor's gives for factorization. You might need to maybe double hash lengths to mitigate Grover's significantly.
Got it. Now, there's this other concept that sounds, well, frankly terrifying. Harvest now, decrypt later. What's that about?
Yeah, it's a chilling idea. It means attackers don't actually need a working quantum computer right now to be a threat.
How does that work?
They can simply collect and store vast amounts of currently encrypted data today. Think sensitive government communications, financial transactions on blockchains, private messages, anything encrypted with algorithms vulnerable to Shor's,
Okay.
and then they just sit on it. They hoard it, waiting for the day when cryptographically relevant quantum computers become available. Once they have one, they can go back and decrypt all that stored data.
So data encrypted today might not be safe in the future, even if it's secure now.
Exactly. It creates an immediate risk for any information that needs long-term confidentiality. That data's time bomb is ticking now.
How urgent is this? When are these powerful quantum computers expected?
It's the million-dollar question, isn't it? Predictions vary, but many experts suggest we might see quantum computers capable of breaking current encryption standards, like RSA 2048, sometime around 2030, maybe a bit later. But nation-states or very well-funded organizations might get there sooner, perhaps in secret. The technology is advancing really rapidly. There's a quote I heard. People don't believe it will happen until it happens. We can't afford that mindset here.
Right. We need to prepare before it happens. So if the foundations are potentially cracked, what's being done? You mentioned two pathways. Let's start with the first, post-quantum blockchains.
Okay. So this first pathway, post-quantum blockchains, or PQB, is essentially about upgrading our current systems with new classical cryptography.
Classical, not quantum.
Right. The idea isn't to build blockchains using quantum computers, but to develop new encryption algorithms that run on our existing computers but are resistant to attacks from both classical and quantum computers.
Okay. So we're swapping out the vulnerable math problems for new ones.
Exactly. These new algorithms, called post-quantum cryptography, or PQC, are based on different mathematical foundations, ones that we believe even Shor's algorithm can't easily break. The focus is mainly on replacing the vulnerable public key schemes like RSA and ECC.
And hash functions, are they?
Hash functions like SHA-2 and SHA-3 are generally considered much more robust against quantum attacks. Grover's algorithm, as we discussed, offers only a quadratic speedup, so maybe you just need to use longer hash outputs. But they don't face the same kind of existential threat as public key crypto from Shor's.
So who's deciding which new algorithms to use? Is there a standard?
Yes, and that's crucial. The U.S. National Institute of Standards and Technology, NIST, has been running a major international competition for several years now to select and standardize PQC algorithms.
Okay.
It's been a huge effort, very rigorous. They announced the first batch of winners ready for standardization. For general encryption, there's an algorithm called Kyber. It's known for being pretty efficient and having relatively small key sizes.
And for digital signatures?
Yeah.
The part needed for transactions.
For signatures, they picked three: Dilithium, Falcon, and Sphinx++. Dilithium and Falcon are also quite efficient. Sphinx Plus is a bit different. It's hash-based, meaning its security relies only on the hash function. It's slower and has larger signatures, but it provides important diversity. Using different mathematical approaches means if a flaw is found in one, hopefully the others are still secure.
Interesting. You mentioned hash-based and Kyber Dilithium Falcon. What kind of math are these new algorithms based on?
Well, many of the leading candidates, including those chosen by NIST, like Kyber, Dilithium, and Falcon, fall under the umbrella of lattice-based cryptography.
Lattices, like a grid.
Sort of, yeah. Think of points arranged in a regular repeating grid in many dimensions. Lattice-based crypto relies on problems related to these structures, like finding the shortest vector pointing from the origin to a lattice point, the shortest vector problem, or SVP, or problems like learning with errors, LWE.
And these lattice problems are hard for quantum computers.
That's the belief, yes. They're considered strong candidates for quantum resistance. And lattice cryptos is really versatile. You can use it for encryption, signatures, even more advanced stuff like homomorphic encryption, which lets you compute on encrypted data.
How does it actually work for public keys?
A key concept is the trapdoor. It's like a hidden shortcut. Certain difficult lattice problems become easy to solve if, and only if, you possess this secret trapdoor information that's your private key. You can make the public key widely available based on the hard problem, but only the person with the trapdoor can easily perform the necessary operation, like decrypting or signing.
Got it. So lattices are a big part of PQC. What else is there besides lattices and the hash-based S-fancy S plus proof?
There are other families too. Code-based cryptography, like the McEley system, uses error-correcting codes. And there's multivariate cryptography, based on solving systems of polynomial equations. NIST is actually looking at standardizing algorithms from these families too, for diversity.
Okay, so the algorithms are being chosen. Are we actually seeing them used in blockchains yet? Or is this still mostly lab work?
No, it's definitely starting to move beyond the lab. There are already projects focused on this. One you hear about is the Quantum Resistant Ledger, or QRL.
QRL?
Yeah, they launched their mainnet back in 2018, claiming to be quantum resistant from the very first block. They use a hash-based signature scheme called XMSS, similar in principle to Sveten plus Jakaba. They're active, working on adding things like proof of stake and smart contracts compatible with Ethereum's EVM, and looking to integrate newer NIST standards like Crystal's Dilithium.
So they're kind of an early adopter. What about established players like Bitcoin?
That's a much heavier lift, obviously, but there is discussion. There's a draft Bitcoin improvement proposal, a BIP, that directly addresses the existential threat, as they call it.
What does it propose? It sounds like a huge change.
It is radical. The proposal outlines phases. First, stop allowing people to send funds to the old vulnerable address types. Then, after maybe 2 years, potentially freeze any coins still sitting in those vulnerable addresses.
Freeze them. Wow.
Yeah, with a possible recovery mechanism using your original seed phrase, but it's a drastic step. It highlights how serious the threat is perceived. A study by Deloitte even modeled what might happen if an attack occurred before mitigation, predicting potential mass sell-offs and market chaos.
So big changes might be needed. Are other blockchain platforms looking at PQC?
Definitely. Hedera has shown interest in Falcon, one of the NIST signature candidates. The enterprise platform Corda already offers SFIN's SES Plus as an option, especially for things needing very long-term security, like digital mortgage or pension contracts. Even Iotia, with its Tangle structure, initially used a type of hash-based signature, though they've changed their protocol since then. So yeah, awareness and exploration are happening.
It feels like preparing for this is crucial. But the threat is still maybe years away, and the standards are just solidifying. How do organizations even manage this transition?
That's where a concept called crypto agility becomes absolutely essential.
Crypto agility.
Yeah, it basically means designing your system so you can switch out cryptographic algorithms relatively easily. Swap keys, update protocols, change infrastructure without having to rebuild everything from scratch.
So it's about flexibility.
Exactly. It's not just for the quantum threat either. Think about vulnerabilities discovered in existing crypto, like we've seen with OpenSSL bugs in the past. Being crypto agile means you're resilient to any future cryptographic break, quantum or otherwise.
What does that look like in practice for, say, a company using blockchain?
It means things like keeping a detailed inventory of all the cryptography you use, automating how you manage keys and certificates, making sure your systems are modular, don't hard-code specific algorithms everywhere, and having processes for regularly rotating keys and updating crypto libraries. It's about building for change.
Okay, that makes sense. Build flexibility in now. So that covers the post-quantum approach, upgrading classical crypto. What about the second pathway, the quantum blockchains?
Right. This is where things get, well, more futuristic, perhaps. Quantum blockchains, or QB, aren't just about making classical systems quantum resistant. They're about actually using principles of quantum mechanics and quantum computing to build the blockchain itself.
So using quantum computers in the blockchain.
Potentially, yes.
Yeah.
Or at least using quantum communication networks. The designs can be hybrid, mixing classical and quantum parts, or theoretically fully quantum.
Fully quantum blockchains.
That's still very much in the realm of theory right now. It's considered pretty unfeasible today because we just don't have the necessary quantum computers or networks widely available or powerful enough. So hybrid approaches, combining classical blockchains with specific quantum enhancements, are seen as more practical in the near term.
Okay, so what kind of quantum tech are we talking about integrating?
One of the key technologies is quantum key distribution, QKD.
QKD, secure key sharing.
Exactly. Protocols like BB84 use quantum properties, like the polarization of single photons and the fact that measuring a quantum state disturbs it, the no-cloning theorem, to allow two parties to generate a shared secret key. The security is based on the laws of physics, making it theoretically secure against eavesdropping, even by a quantum computer. QKD could secure the communication channels between nodes in a blockchain network.
Interesting. What else?
Then you have ideas like quantum signatures. Here, the public key might be derived from a private quantum state. Verifying it could involve something called a swap test using quantum mechanics.
Sounds complex. Are there challenges?
Oh, definitely. One big challenge with quantum signatures is related to something called Halebe's theorem. It basically limits how much classical information you can get out of a quantum state. This practically limits how many copies of a quantum public key you could reliably distribute, which is a major hurdle for a large decentralized network.
Right. Scalability sounds like an issue.
A huge one. Other concepts include using quantum teleportation, leveraging entanglement to transfer quantum states between nodes. Although remember, it doesn't allow faster-than-light communication, you still need a classical channel. And researchers are exploring quantum consensus mechanisms, maybe using true quantum random number generators for leader election, or adapting classical agreement protocols like Byzantine agreement for quantum networks.
This all sounds incredibly advanced, almost sci-fi. What's stopping these quantum blockchains from taking over?
Well, several major hurdles. First, the sheer complexity and the costs are enormous. Second, compatibility with existing systems is practically non-existent. But the biggest roadblock is simply the state of quantum hardware.
We just don't have the machines yet.
Exactly. We don't
Right.
have powerful, stable, accessible quantum computers or the widespread quantum networks needed to run these things at scale. Most of the work is theoretical or maybe small-scale proofs of concept in labs.
So it's very early days for this quantum path.
Very early days. The current quantum blockchain proposals are often quite simplified compared to classical blockchains and aren't really competitive yet in terms of features or scale. Building the required infrastructure, like reliable quantum repeaters for long-distance entanglement distribution, is still a massive engineering challenge. They're mostly lab curiosities for now. So, stepping back and looking at the big picture, both of these pathways, the post-quantum upgrades and the longer-term quantum blockchain concepts, are really vital research areas for securing decentralized systems against the quantum future.
How do they stack up then in terms of feasibility?
Well, to summarize, post-quantum blockchains, the PQC approach, seem the most straightforward to adopt and scale relatively soon. They build on infrastructure we already understand, even though the cryptographic migration is a huge task. Hybrid quantum blockchains, mixing classical and quantum elements, face moderate challenges needing some quantum components, like QKD links perhaps. But fully quantum blockchains, they're currently the hardest to adopt, requiring significant breakthroughs in quantum hardware and networking. That's the long-term frontier.
It really sounds like the future isn't just one or the other, but maybe a mix, evolving over time. And it strikes me that this isn't just about crypto coins, the encryption we're talking about. It secures pretty much the entire internet, right?
Absolutely. Online banking, secure communications, government secrets, corporate data, it all relies on the same types of public key cryptography that blockchains use. So this quantum threat isn't a niche crypto problem. It's a fundamental cybersecurity challenge for our entire digital society.
Wow. Okay, so we've covered a lot today. We've gone from how current blockchains work to the looming threat from Shor's and Grover's algorithms, explore the practical post-quantum crypto solutions being standardized now, like lattices and hash-based signatures.
Right, and touched on those more futuristic quantum blockchain ideas, using things like QKD and quantum entanglement.
It's definitely a field moving incredibly fast,
Yeah.
from potentially broken crypto wallets to mind-bending physics.
I think the main takeaway for you listening is pretty clear. We don't know the exact date quantum computers will break today's crypto, but the need to prepare to transition to quantum-resistant solutions. That's not an if, it's absolutely a when.
Both approaches seem important. The PQC fixes we can deploy sooner, and the longer-term research into quantum-native systems.
Exactly. They're both crucial pieces of the puzzle for securing our digital world going forward.
So, maybe a final thought for you to chew on. As quantum computing keeps advancing, what do you think will be the biggest hurdle in securing everything? Is it the sheer technological challenge of building these new quantum-resistant systems or quantum computers? Or is it more of a human challenge, getting everyone to adapt, to upgrade, maybe even to perform difficult hard forks on massive networks before it's too late? Because, like that quote said, people don't believe it will happen until it happens. And waiting until it happens might be catastrophic.